Okay, hello, this is Josh Ring, and this is part 4 of the video. So in our previous section, or previous part, we had this exact same equation, CV, natural log of T1, or T2 over T1 equals negative R of the natural log, and we had V2 over V1. But for this, we're going to want to change it up a little bit. So we're going to use the ideal gas law where we have V equaling to RT over P. We're going to substitute that in, for the volumes, which is then going to leave us T2 over P2 times T1. I'm sorry, P1 over T1. My bad on that. And the R's from the V equals RT over P cancel out. So next we are going to move the CV over to we are going to take the constants and move them to the other side. This one's already out in front of the natural log, so we can move it over to the other side, and then this one will go up in the what am I trying to say? In the exponent. So we are going to then have the natural logs will still stay for this, but we're just going to move the coefficients. So natural log of T2 over T1 is equal to negative R, and then in parentheses we'll have here what am I trying to do? T2 over P2, and then P1 over T1. And then this will be to the power of the negative, this isn't supposed to be R, this is supposed to be natural log. And this will be the negative R over CV. And then this, by moving the CV to the other side, this will leave us with a coefficient on this side of R over CV plus 1. But in this case, we can use gamma instead, so we don't have to keep writing that out. So now in our next step, we are just going to get rid of the natural logs. So that's going to look like this. We'll have T2 over T1 to the gamma. And then on the other side, we are going to have T2 over P2 times P1 over T1. And then once again, it's to the negative R over CV. And then by combining like terms, we can get the the T2s and this T1 over here to cancel out with some things over here. So it's going to end up looking like we'll just have a basic T over T1, and this is still to lambda, and then we'll have it equaling to P over P1 to the negative R over CV. And everything's looking good for now. Calling how I got the lambda here for the 1 plus R over CV, that is also equal to, I'm just going to do it here up in the corner, lambda is also equal to Cp, which is the heat capacity for constant pressure, over Cv, which is the heat capacity for a constant volume. That will just come into play a little bit later, but I just wanted to point that out for now. Then, actually, no, I'm sorry. That's important to the next step. It's also equal to the, like I said, 1 plus R over CV. So we're going to use this to this negative R over CV, and we'll be able to simplify the equation to T2 over, just T. We got rid of the T2 earlier. It'll be T over T1, still to the lambda, but this side changes up a little bit. We still have the P over the P1, but we are going to change the negative R to CV to be lambda minus 1 by using this like I stated earlier. And now we are just going to get the t's all alone, so we are going to get rid of the lambda. So we'll have t, should be in uppercase, t over t1 is equal to p over p1, and this will be now to the power of lambda minus 1, which we had before, and then when we bring the lambda over to the other side, it will now be divided by lambda. And finally, we are just going to solve for t, so we can just have our basic temp, which is going to be equal to, just moving the t1, multiplying, excuse me, the t1 to the other side. We'll have t1 times p over p1 multiplied by lambda minus 1 over lambda to the power. I'm sorry, not multiplied, to the power of. So that ends it per part 4, and I will see you next on part 5.